Morning, everyone. So we finished part one of our acid-base chapter here. Believe it or not, this is only half of the chapter, but we'll just sort of wrap it up there. I was hoping to just give you a quick summary of some of the major highlights that we had. I definitely introduced a lot of the vocabulary, a lot of the different definitions of acids and bases. Some of this vocabulary will carry over into part two, so make sure you're comfortable with this one here as we continue stepping forward. So just a quick rehash here. We started off the part one of this section here with what's referred to as the Arrhenius definition. Arrhenius definition is the one that we all know. I'm going to set up a quick table for you here. What does it mean to be an Arrhenius acid, or what does it mean to be Arrhenius base? In this case here, an Arrhenius acid is it's some chemical that ends up releasing H plus in solution. So the characteristic acid particle here is H+, and this is an ionic chemical. Usually we just say HA because either it's one-way arrow or even in equilibrium. It's able to not just have an H inside of it, but when you drop it in water, it ends up releasing, giving up this H+ here. For a base, in a similar fashion here, I want you to give up the characteristic base particle, so release OH- in solution. We can always assume that the background of solution is just water, so that's why we were typically going to be something like BOH. Again, doesn't matter one-way arrow or equilibrium arrow, but basically we're going to get some ion, and then we're going to have released hydroxide. So that was the Arrhenius definition. We found that that was a little bit too restrictive because this one here really didn't help you explain how come ammonia is also a base. Ammonia, like NH3 as an example, NH3 also manages to get hydroxide, and yet NH3 doesn't actually hold the OH- inside of it. So what we did in the first section was we started switching over from the Arrhenius definition. We switched over to something called the Bronsted-Lowry definition. Even this is not the biggest definition for it, but we started looking at Bronsted-Lowry. Basically, an acid-base neutralization, when they cancel each other out, we started looking at it as one proton transfers. Remember, a proton is synonymous with an H+. I'm just going to give you this definition first. Bronsted-Lowry acid here, the definition hasn't changed much. You can just say it donates an H+ in solution. Well, an H+ is the same characteristic acid particle here, very similar with Arrhenius, but a Bronsted-Lowry base is totally different. A Bronsted-Lowry base actually has nothing to do with releasing hydroxide. It actually just accepts an H+ from solution. And in that case there, the acid's job is going to donate the H+. The base's job, upon grabbing the H+, it ends up releasing off hydroxide. So it's still consistent, but it's just a little bit more broad. So let's just try out a question or two here. Let's try HC2O4- reacts with SO4-2. Okay. So the question here is, can you predict the products? Can you tell me which way the proton transfer goes? So in a situation like this where it's a little bit more obvious, this one here, it's a chemical that has a hydrogen that has a negative charge here. This one could be amphiprotic, an amphiprotic substance. An amphiprotic substance can be acid or base. So right now here, this one here could donate a football, could donate an H+, or because it has a negative charge, it can actually gain an H+, and it can actually become neutral as a charge. So this one I'm not sure yet. It could be acid or base, but definitely looking at the other compound, because SO4-2 has no protons, this one has to be the base. So while the hydrogen oxalate here could be acid or base, because it realizes this one here is waiting for the football, it's going to say, okay, I'm going to be the acid here, I'm going to have the H+, and I'm going to toss my football over to SO4-2. So what's going to happen to the hydrogen oxalate is it's going to go down by an H, go down by a charge. We're going to end up just getting oxalate, C2O4-2. The SO4-2, in contrast, is going to pick up the football, going up by an H and going up by a charge. HSO4- like that. All right? So that's that one proton transfer here. Remember, we use that terminology. We always have to have one acid and one base on both sides. One person willing to toss the football, one person willing to gain the football. Now, the hydrogen oxalate and oxalate are referred to as conjugate pairs. As a conjugate pair, they are species that differ by one proton, just by one single H+. The conjugate acid is currently the one that has the proton, currently is holding the football. So HC2O4- is the conjugate acid in this case here, the C2O4 minus partner, which is on the opposite side. Conjugate pairs are on opposite sides of each other. The conjugate base is actually without the proton. It's after I toss the football away. So that is one conjugate pair. Even the SO4 minus 2 and the HSO4 minus also forms a conjugate pair where the HSO4 minus is also the acid. Potentially this one here has a football. I can toss the football back over. Okay. A lot of these equations here end up in equilibrium because a lot of these are weak. So we're going to look at a table in a second here. But I just wanted to rehash also. Throughout this chapter, we've been mainly focusing on this proton. What is an H+? Why am I constantly calling it here a proton? Well, if you look at the hydrogen atom, hydrogen is one proton. It actually has no neutrons for the most stable isotope. Hydrogen would have had its one electron. In becoming an H+, it would actually have lost this electron here. So going from hydrogen as an atom, which had the size of being one shell out, an H+ is very well just a proton. So an H+ is just a proton. You'll notice that it's a very dense positive charge here. In water, it's not going to stick around like just a single H+. So when you toss this H+ here into water, what's going to end up happening is water, the chemical name for this is it actually acts as a ligand or a Lewis base. And basically water, although water is a neutral molecule, because the oxygen end is kind of negative, the hydrogen end is kind of positive, the water actually helps to stabilize the H+. So we actually get this equilibrium setup here where the H+ gets complexed with water, gets reacted with water. This is also in equilibrium and ends up forming a compound called H3O+. H3O+ here is given many names. You can call it a hydrated proton here. The most common name here is a hydronium ion. So throughout this section, we started being pretty sloppy. Oh yeah, H+, yeah, it's basically hydronium. That's because in water, basically the water has actually complexed with H+. It's made a much larger molecule. It couldn't get rid of the positive charge. But if you think of the positive charge as being unstable like a hot potato, instead of the H+ holding onto the hot potato itself, at least becoming a much larger compound like hydronium, at least the entire molecule can hold onto this hot potato. You can trade it around, pass it around the different atoms. So throughout this section here, we've been calling an H+ a proton, and especially in water, a proton is actually hydronium. Okay? How do we know which ones are equilibrium and which ones are strong? We're going to look at the acid or base strength. Strong actually refers to the degree of ionization. A strong thing is 100% ionized or 100% dissociated, 100% broken up. So in these sections here, we want to have a one-way arrow. These are definitely not going to form an equilibrium. Contrast that with something that's weak. Weak technically would therefore mean something that's less than 100%. Even 99% dissociation or ionized, this one here would actually be weak. But on our table, it actually relatively talks about some things are still better at donating protons. In general, we're looking at maybe 5%, 10% dissociation. The constants are actually very, very tiny. So in this case here, we're going to end up with an equilibrium arrow. Let me just give you just an example of this one here. You don't need to memorize your strong acids. This one here is on the table. Your table actually lists for you acids on the left column, and we had the strength of acid increasing, let's say, acid strength. As you go up to the table, the very top 6, so HCl, HBr, those ones there are definitely strong acids. You see that they are all one-way arrow. Because I know HCl is strong, it completely reacts, completely dissociates to become H+ and Cl-. So putting some numbers to this here, let's say the HCl is 1 molar. Breaking off completely, you're going to get 1 molar H+ and 1 molar Cl-. Even though I show my work like that, it is understood that the HCl is no longer holding hands. That compound is completely ripped apart to form H+ and Cl-. Really easy to find the amount of H+ in solution, one-way arrow. Let's contrast that with a weak acid instead. A weak acid here like Chaku, all the reactions, so you're going to see Chaku on the table, somewhere lower. Definitely it's not in the strong acid section, it's in the weak acid section. But still we have this relative ordering of strengths here. CH3 here is not as good as the acids above it, it's better than the acids below it. Being weak overall, we know it's equilibrium. Its job is still to donate a proton, H+, we're going to end up forming our acetate ion. But being weak, if you actually quote the Ka constant, let me just look up the Ka constant for this particular acid. The Ka constant is actually 1.8 times 10 to the negative 5. In general, you're going to find Ka. Ka is basically KEQ. KEQ is supposed to be products over reactants, we have the A because the CHQ is actually acting as an acid in this situation. Because we're dealing with numbers that are so tiny, this tells us whenever KEQ is actually less than 1, it tells us reactants are favored. It tells us we have a lot more reactants than products. So even if we started off with equal molarity, let's say also 1 molar CH3COH, because reactants are favored, not a lot of it chips off to actually become H plus and CH3CO minus. In part 2 of this chapter, we'll actually deal with ice tables. We'll actually calculate how little the H plus is, but just noting, well, because we're only expecting this to ionize maybe 5%, 10%, maybe the molarities I'm looking at, totally making up some numbers here, maybe I get 0.01 molar, 0.01 molar. It's only a really, really tiny corner, a tiny fraction that actually goes over to the other side. At first, when you look at those numbers, you'll say, wait a second, then the mole ratio doesn't work anymore. Well, the mole ratio should be 1 to 1 to 1. Shouldn't it be 1 molar, 1 molar, 1 molar? It's not that the mole ratio is broken. We actually have exactly lost, let's say 0.01 molar has actually broken off. For 0.01 molar, you got 0.01 molar H plus, 0.01 molar acetate. It's just looking in general, I still have it heavily favoring the reactant side. Okay, so the mole ratio is still fine. It's just not as easy to actually get the H plus. Once you get to H plus, you can use that box diagram to actually get to hydroxide and all the other values. They might ask you a question in terms of conductivity. So electrical conductivity here, remember from our last chapter, for conductivity, we need to have charges and they need to be mobile. And in fact, the more charges that are mobile, throughout this section here, we're dealing with ionic compounds. So the ions that form the compounds here would be the charges. In general, if I have more charges, so the more ions that I have in solution, the better things break up. More ions actually means more conductive. So just if I played fair, equal molar of strong acid, strong base, a strong acid will give you the net of about 2 molars worth of ions. If I only have 1 molar weak acid and this ionizes really poorly, I only get a net of about 0.02 molar here. I would expect strong things to ionize better than weak things. However, sometimes I play not fair. Sometimes I just have, what if I compare 0.0001 molar HCl? This one here is still a strong acid because chemically speaking, this one still breaks 100%. It is a very dilute sample though. It is one in which I've actually added a ton of water. What if I compare that against 20 molar, I don't even know if you can get it up to that high concentration, of acetic acid? Is it possible that the weak thing may conduct more? Well, this one here, HCl breaks off 100%. This becomes H plus and Cl minus. It's just that I was so dilute to begin with, I might really well only have very low molarity, low number of charges. Even though this weak acid here is not really good at ionizing, because I started off with a very concentrated sample, so I'm just rehashing there. You don't want to use terminologies like strong and weak to refer to concentration. You can just say high molarity or concentrated. Even if this one here is in equilibrium, even if this one doesn't break off to become H plus and acetate very well, because my starting concentration was so high, even if I get only 5% of this, that might very well end up being, I can totally make out numbers. Maybe I get 0.5 molar, oh look, I have more ions, the weak thing could actually conduct better than the strong thing. But that's only when we played really unfairly. Definitely if these are equal molar, there's no contest, the strong thing would win out. Okay. For strong things here, they actually give us on our table a bunch of Ka constants. If this one here were in equilibrium, if I tried to do a products for reactants, I pretty much have it ionized 100%. I have all products. I essentially have 0 reactants. If I try to divide by 0, they're just going to say the Ka value is actually very large. So the Ka is this KEQ constant. The larger the number, the more the products are favored. In general, we're going to see most of our Kas as actually something that's less than 1. In fact, all strong acids in water, they break up 100%. So what water does is water ends up leveling the strengths of these acids. Even though for these top 6 here, even though one of them is above the other one, it doesn't mean relatively they're stronger than each other. All of them are actually equal strength. We're going to say water has leveled the 6 strong acids, those top 6 on the table here. Water has leveled the 6 strong acids to the same strength because all of them are equivalent to an H plus solution. So imagine starting off with HCl. As a strong acid, I'm supposed to give up an H plus, give up a Cl minus. So once you hit water, it 100% reacts. The H is no longer holding hands with Cl. What if I have HBr? HBr, wait, it's a different chemical. But HBr, upon dropping in water, it too forms an H plus solution. Sure, the counterbalancing ion is different, but it's equivalent to an H plus solution. So that's why they like asking this question as well. What is the strongest acid that can exist in solution? It's actually H3O plus. In solution, water would have actually separated positive from negative, leaving you behind just a proton. H3O plus is the very top acid in the weak acid section here, and this one here has a Ka of 1.0. Right? That's as strong as you can get it. So hydronium is equal to H plus and water there. Okay, so H3O plus is the strongest acid in solution. Similarly speaking, this whole table is in favor of sort of acid strength. It tells me how good this left-hand molecule is in going forward. As I get weaker and weaker in going forward, my partner, my conjugate base, which is on the other column here, my conjugate base here has, at first it had a really hard time coming backwards. My conjugate base is actually getting better and bigger coming backwards. So we actually have increasing base strength as I go downwards. So increasing basicity or increasing basic strength. To the extent of when I get to the really, really far down, we actually do get a one-way arrow. The strong bases that I have are actually just oxide, O minus 2 and an amine, NH2 minus 2. Again, you don't need to memorize that. Those ones there, one-way arrow, they react with the H plus and they become the OH minus, the characteristic base molecule, or even ammonia. Now you say, wait a second, I thought hydroxide and ammonia themselves were bases. You're going to actually find hydroxide is actually a weak base. When hydroxide is under the base column, it too can grab an H plus and it can actually reform water. That equation was given a special name that was called the self-ionization of water, and if you totally blank out and you forget what the Kw value is, the Ka for this equation is the Kw, 1 times 10 to the negative 14. So overall, this table, we had this middle section here, all of them were equilibrium, all of them were weak, but relatively speaking, some of them still ionized better than others, so they were still a little bit higher than the other values here. We're going to cheat a little bit here. Well, this is actually a really short list of strong bases. I just have O minus 2 and NH2 minus. It also gets leveled by water. Those two are equal strength. They're equivalent to a solution of hydroxide in solution. But OH minus is actually the strongest base. Once I've actually gained that proton, once I've actually formed hydroxide, that's the only leftover base in solution, and that itself is actually a weak base. We're going to add to our strong base category here as a strong base. It's definitely these two here, O minus 2 and H2 minus 2. But I'm also going to include any soluble salts that contain OH minus. So NaOH, calcium hydroxide, lithium hydroxide, anything with hydroxide that I know is fully soluble, it's going to one-way arrow. It's also like a strong base. Complete reaction is going to produce hydroxide. So therefore, it's a strong base as well. So those two, including any soluble salts with OH minus. Let's just rehash here. We did introduce a little bit of Ka and Kb. At the end of the day, they were KEQ. Ka is the acid constant if the thing is acting as an acid. Kb is similarly for a base. Let's just do our example again. Let's do our Chiku. On the table, unfortunately, all our reactions have been simplified. They basically says, as a Bronsted-Lowry acid, this one here is supposed to donate a football. Well, donating a football, I'm going to lose that H+. I'm going to go down by an H, go down by a charge. That's what ends up forming acetate. This one here has been a simplified equation. Just to look ahead to part 2 of this chapter, you will always need to convert it to the complex equation before we're ready to do ice tables. How do you convert to complex equation on the acid side? It's like adding water to both sides. No real chemistry in this one here. This is just a nice hint. How do you get from one reaction to the other? So what it's saying here is we have CH3COH in equilibrium. React with water. This one here is in equilibrium. H plus will react with H2O, end up forming H3O plus and CH3COO minus. I'll show you what we said in terms of the picture here. The simple picture was, you toss in this Chiku into solution. All that's going to happen is it's going to equilibrium. Some of it's going to break out to become H plus. Some of it breaks out to become acetate. Well, we just said H plus is a really dense positive charge. It doesn't look like this in solution. So yes, the acetic acid has donated a football. Who did it donate the football to? Oh, the football actually gets passed to some water molecules that are close to it. as the water molecule is complex with the H+, that ends up forming hydronium. Basically, we look at this as a 1-proton transfer. The acid donated the football over to the base. Water picking out the proton goes up by an H, goes up by a charge. This is now the conjugate acid form of water, and then we have the conjugate base form left over as acetate. Always one acid and one base on both sides of the table. And that's what the complex equation tells you. That was on the acidic side. Let's do something similar here on the basic side. So let's do ammonia. On the table here, the bases are on the right-hand column. So if you want to look at base strength, you just look at this right-hand column here. You will find ammonia partway down. For a base reaction, I need to think about ammonia picking up the H+ and actually going in reverse, going to the left. So I read right to left, although I'm just going to flip that around here. I'm going to write ammonia here as a reactant. If I read left to right, my simplified equation just says, as a Bronsted-Lowry base, you are supposed to attract and accept the proton. All right, so I'm going to grab this proton here. I'm going to go up by an H, go up by a charge. The only problem here is there aren't a lot of free protons swimming around the solution. You can drop in ammonia, right? So I drop in NH3. We actually calculated how much H+ there was. H+ is roughly about 10 to the negative 7 molar at 25 degrees. So 0.00001 molar, right? So although, yes, NH3 here as a weak base is supposed to be grabbing this proton, there aren't a lot of protons in solution. So the simple picture here is a little bit too condensed. What you want to do is you want to convert it over to complex form. Again, this is nice practice for what we're going to do in part 2 of this chapter. Going from the complex form on the base side, it's pretend you add hydroxide to both sides. Right? It's going to stay balanced if I do the same thing to left side and right side. Well, what's going to happen then is NH3 is going to be able to pick up proton, but by adding the hydroxide, H+ and OH- ends up forming water. It actually tells me the more plentiful thing in solution is actually water. Water as a pure liquid is about some 50 molar or so. NH3 in the presence of water is actually going to steal a proton from water. Yes, at the end of the day, it's a Bronsted-Lowry base, it accepts the proton, but stealing from water, it ended up becoming NH4+. It's actually water that ends up leaving behind the characteristic hydroxide particle. So more than just the Arrhenius definition for the base, I don't need to have a soluble salt containing hydroxide. I just need to steal from water, and actually water is going to leave behind hydroxide. Water, we've seen an example here. Water is currently acting as an acid because NH3 wants to be the base. Previously, water was the base, so again, we refer to that as amphiprotic. It could act as acid or base. Typically, something that has an H, usually you'll have a negative charge so that you can pick up an H+. Okay, so that's where we're going to be starting off part 2 of the chapter. We're going to write out the complex equation, what's actually happening. That way I can track OH- for a basic solution, and later on I can end up doing ice tables. We're going to do that in part 2 of this chapter. Remember, we've ended up forming 2 conjugate pairs. The conjugate partner that doesn't have the football yet is the conjugate base. So NH3 and NH4+, this is the conjugate acid form. Water as a conjugate acid, as it becomes OH-, that's the conjugate base form. Conjugate pairs differ by 1 proton, and we're going to have 1 of each on either side. Okay, so make sure you're comfortable converting sort of the acid form to the base form here. Let me just demonstrate this for you here. Let's take our acetic acid. So far, I've just been reacting acetic acid with water, or ammonia with water. What if I put acetic acid directly into a solution of NH3? They're going to ask us to predict the products. Well, both of these were weak. Both of these were in equilibrium themselves. So overall, this is going to be in equilibrium. This time, instead of acetic acid tossing the football just to water, this time the football gets tossed to NH3. Always really easy to predict these reactions. The acid is going to go down by an H, go down by a charge. I'm going to get acetate. And the NH3 is going to go up by an H, go up by a charge here, and we're going to end up with NH4+. So this one here was a little more obvious because this can only be acid. I don't want to pick up another proton. This one here can only be base. And again, we've ended up forming, now I have the conjugate base form of acetic acid and the conjugate acid form of NH4+. What's interesting here is, while it was obvious who's acid or base at the beginning, now what I've done is I actually created another acid, right? The NH4+ wasn't there before. Now the NH4+ has a football. Being in equilibrium, the NH4+ could toss the football back. So in this question, they can actually ask you, can you find for me what is the KEQ expected to be? Is it going to be products favored or is it going to be reactants favored? In this case here, we're going to go to our trusty table. Because our trusty table only gives us Kas, let's just compare the acid strength. Similarly, you could have compared the base strength as well. The Ka for CH3COH, I'm going to look it up on the table. This constant was 1.8 times 10 to the negative 5. The constant for the ammonia, NH4 plus, look at it for the left-hand side. NH4 plus is actually 5.6 times 10 to the negative 10. So although, yes, both of them can be acids, because this constant here is bigger, it was definitely bigger than NH3. NH3 doesn't want to be an acid, but it turned out it even is bigger than NH4 plus. We have the stronger acid. It's still a weak acid, but we have the stronger person on the left-hand side. If they do their job better, don't say this side is favored. If the stronger volleyball team is on this side, they're going to hit the volleyball to the other side of the court way more often. There's going to be way more products at equilibrium. So I have a stronger acid on the left side. So in our terminology, we can say products are favored. And what that means is it just means we have more products at equilibrium. Equilibrium was supposed to be this balanced state. The concentrations are constant in time. That's all true. Forward rate equals reverse rate. All that's true. But even at equilibrium, we have a situation because I had the better team on the left side. I don't say that side is favored. They do their job better. They're going to toss the football better, and they're going to knock the equilibrium way over to the right-hand side. So if KEQ in general here, right, I don't do just Ka and Kb. We have too many acids and too many bases to actually look at here. If KEQ in general is a products over reactants, and you've now decided, well, there's more products, the higher the numerator, the lower the reactants, that means KEQ is very large, so KEQ is actually bigger than 1. If we ended up forming an acid that was actually stronger than my acetic acid, the stronger team on the right side, I'd say reactants are favored. If the reactant value is bigger, the KEQ is something between 0 and 1, less than 1. Through our lessons here, we were able to actually take Ka of the reactant acid divided by Ka of the product acid to actually find what the number is. But typically, if you can just identify, is it bigger than 1? Is it less than 1? That's all you would need. Okay. Let me just finish off the summary here. We started introducing a little bit of the math as we started getting to pH, pOH, those sort of calculations. We can just sort of summarize that a little bit here. First thing is you need to know this equation called the self-ionization of water, also called the auto-ionization of water. And pretty much what it implies here is this is endothermic. It's water having the slight ability to self-ionize, to just break up naturally. The equilibrium constant for this one here is called Kw. So it's going to be products over reactants. It's H plus times OH minus. In this case, because water is a liquid, remember we always ignore pure liquids, so I don't need to include that in my Kw expression. This one here is a constant, 1.0 times 10 to the negative 14. You're going to always assume your questions are at 25 degrees. That actually sets 7 as the dividing line as neutral, but that's only true again at 25, which we're pretty much always going to be at. Pretty much what's happening here is if I just take a solution of just water, I would have expected all of the particles just to be H2O. What this self-ionization tells me is water has a slight ability to form H plus and OH minus, but because this constant here is so small, that actually means reactants are favored. That means the concentrations of H plus and OH minus are actually really low. So if I start off with just pure water is another way of saying neutral water. And neutral water will definitely have H plus particles, OH minus particles, but what's happening here is pure water has an equal number of H plus and OH minus. So if I sub in, let's say, an X times an X, and we're supposed to equal 10 to the negative 14, we're going to find in a neutral solution, the concentration of both of these are actually 10 to the negative 7 molar, 0.0001 molar. Really, really tiny. So although water does have this capacity to self-ionize, it doesn't do it very well. What we're going to do now is we're going to throw in some acid. So let's throw in HCl. And I'm not going to worry about dilutions for now, but let's throw in 3 molar worth of HCl. Okay? HCl is a strong acid. So this one here is going to be one-way arrow. The Ka constant is going to be ridiculously big. It's just going to say very large on the table. So I drop that in there. Suddenly I increase the H plus by a whole lot. It used to only be 10 to the negative 7. Now it's 10 to the negative 7 plus 3 molar. What's going to happen here is this one here is going to go upwards. Because the H plus has gone upwards, seeing as I still need to multiply to give the same constant, we have an inverse relationship. The hydroxide will need to drop. It already was very tiny to begin with, but it's going to drop even lower than 10 to the negative 7. So we sort of worked out this diagram here. If you want to go from H plus and you want to go to OH minus, the expression connecting these two here, water will make sure that the OH minus satisfies this equation. What is the OH minus when the H plus is actually 3 molar? I can just sub in 1.0 times 10 to the negative 14 for Kw My H plus currently is 3 molar. Yes, it is 3 molar plus that 10 to the negative 7, but that value is so tiny, practically it's 3. You can figure out what the hydroxide is in this situation. So let's just do that here. We're going to have 1e negative 14 divided by 3. My hydroxide concentration this time is, let's say, 3.3 times 10 to the negative 15. My H plus is just 3 molar. An acidic solution is just one in which your H plus content is higher than the hydroxide. Because sometimes we're dealing with really, really tiny numbers, I already was 10 to the negative 7, and now I've lost a factor of 10 to the 7, so another million times less hydroxide particle, because I want to avoid having these really tiny 10 to the negative kind of numbers. What we started doing is we started converting it over to pH and pOH. These are just the names of two rulers here. P anything means power of that thing. For the power of that thing here, we're just going to go negative log of the H plus, which is negative log of 3. On the other side here, we can take the negative log, and we're going to see mathematically, you may not have done logs in your math classes yet, but pretty much as a button on your calculator, you just type negative log that number. It just reconverts it here. The corresponding pH for my numbers was negative 0.48. Remember, for pH, pOH, pKW, all the significant digits are after the decimal place. So 3.0 has 2 sig figs. I want to make sure I have 2 digits after the decimal place here. If I take the negative log of this 3.3e negative 15, give or take a little bit of rounding, I'm getting 14.48. Again, significant digits after the decimal place. So just to summarize a little bit of the math, we'll still use this box a lot in part 2 of this chapter. It's going to be a little bit more work to get to a number like H+, but once you have the H+, you're more than welcome to use this box here to sort of reframe that. If the H+ is this, what's the hydroxide? What's the pOH? Where am I on the pH ruler? We found that in general, the relationship was pKW is equal to pH plus pOH. Again, if you can assume 25 degrees, the pKW was just 14. So you can just go 14 minus. If I go 14 minus a negative 0.48, that does give us 14.48. Okay. Remember, pH here is a logarithmic scale. Usually 7 is a dividing line, but again, only at 25 degrees. Sometimes they're going to ask you, how come pure water has pH 5, pH 8? It's probably because we're not at 25 degrees. The lower the pH number, the more acidic it gets. So pH decreases actually means more acidic. So more acidic. As the pH, as this number drops, as the pH increases, we're actually going to the basic side. But remember, this one here is a logarithmic scale. We saw that in the math here. Well, I put the log in the formula. A logarithmic scale is basically an order 10 kind of scale. So even though the steps look evenly spaced, in fact, a pH 6 is 10 times more acidic than 7. A pH 5 is 100 times more acidic. You have 100 times more molarity of H+. It's getting increasingly hard as I step away from this neutral line here. So usually we ballpark around 0 and 14. We just happen to have a very strong acid, HCl, a fairly decent concentration like 3 molar. So we've actually pushed slightly into the negatives, but it's pretty hard to get far past that. We run into sort of saturation sort of problems. That is a pH scale. pH is just a name for the ruler. Depending on where I am on this ruler, yeah, I could be acidic or I could even be basic. In a similar fashion, pOH, we did that relationship that they always had to add to 14. Again, we ballpark it, 7 is neutral. Between 0 and 14, it's sort of like a flip of the pH scale. We actually have basic when the pOH is actually less than 7. It's actually acidic when it's actually bigger than 7. And then basically the pH and the pOH always adds up to 14. So just be careful. Yes, pH watches H, pOH watches OH, but this is just the name of the ruler. I still can say, depending on what my number is, yep, pOH is 3, basic. Yep, pOH here is 10, acidic. Right? Just let me end off as well. This is negative log that gets us to this power of kind of frame of mind. Going the other way here, I need to get rid of the negative, get rid of the log. You can say in words, anti-log, be careful to do negative pH, or most of the calculators here will have it worded, a logarithm here is an exponent function, so it's actually 10 to the power of negative pOH here. Okay, so definitely practice through some of these calculations. We'll do a lot more of this in part 2 of this chapter. If you have any questions, let me know. Thanks, guys.